something strange on the screen. That's why I feel need to ask. So, and this is the Turkey seismic hazard map. As I mentioned, it has been published in 2019. So after I will talk about in the first part the one earthquake, which was a big earthquake and struck many buildings and damaged many historical buildings, residential buildings, and also has impact on the soil on the soil. And so you can read the article that we published. Okay, hopefully you can see. I will continue. Yes. Okay, so the one is located southeast part of the Turkey. Okay, and this in this map you can see the fault lines. These are the active fault lines located in Turkey. So we can say that is a there is high seismicity. And this is the North Anatolian fault. This is the East Anatolian fault, and you can see some other small faults acting on the west side of the Turkey. And in 23 of October 2011, one earthquake occurred in the system on a fault that was not mapped on the active fault map. And therefore, the observation of the site becomes much more important than the other earthquakes. The major tectonic structures in Turkey are well studied on the North Anatolian and kind of East Anatolian fault zones, but still there are unknown faults which are not mapped. So USGS announced the strike dip and rake angles like 241 degree, 51 degree, and 58 degree respectively for the tectonic stress field in the area. So this is the map of the one. Okay, you can see the historical earthquakes that happen in this region, and the red ones are the historical one, and the yellow ones are the instrumental ones.
Excuse me, ma'am.
Yes.
Presentation is not. We cannot see the presentation.
Actually, it looks I'm sharing.
It is already shared.
Can you see that now?
Yes.
No, ma'am.
No. Actually, it looks like that I'm sharing it.
You are seeing the presentation.
Yeah, so in the presentation or in the presenter notes? Do you see the full screen or the presenter notes?
Hello, good morning, Hatu. It is visible now. It is visible now. Yeah. Go ahead.
Okay, so I continue. Yes. Actually, this is the map that we obtained the historical and the recent earthquakes, which are instrumentally recorded from the Boğaziçi University and also from one paper. So this is the special distribution of the PGA of the instrumentally recorded strong ground motion stations. You can see, and the dark one is for which is close to the epicenter. This is the epicenter, and in here, this is the epicenter. Sorry, I'm working on the wrong screen, I think. And this is the maximum PGA that occurred. Okay, the interesting thing on the one earthquake is that you can see the football and handball, but you can also see the site amplification at one of the stations, like in Bitlis. And another tough part for the one earthquake, excuse me? Okay, so the another important part, we can see the site amplification for the region by looking at the recorded ground motions for the, especially for the Bitlis, in the Bitlis part. And as I mentioned, this fault line is not recorded or mapped in the fault maps for Turkey, especially for the East Anatolian part. And it's around 0.2 G for the PGA and 26 centimeter per second for the velocity, for the maximum. And this is for the PGV distribution. You can see the same pattern, but this time in the velocity, these two becomes a little bit higher than the others. And this is the village towns visited in the field are shown with the full circles, okay, for the residential, let's say, buildings, and the bridges with the arrows. These arrow lines shows the big bridges observed during the after the earthquake, and the historical places with the empty triangles, like this one and this one. So, and you can see the legend with the from damage from none to the severe. So you can see the information on strong ground motion stations that that are recorded during the earthquake, okay? And some sites information, soil informations are observed from the stations, and these are approximately same as the NIARP B and C, maybe, let's say. So, to further investigate the characteristics of the recorded ground motions, we evaluated the GMP relationships to be able to predict the PGA values for the region. And we have looked at the Kalkan and Gürkan, Ulusay et al., Akkar and Bomer, Akkar and Canan, and Boer and Atkinson, denoted respectively as KG04, UTL04, AB10, AC10, and BA08 in the following slides. And you can see this, the PGA values and the period at 0.2 and the period as at 1 second for the hazard curves, let's say. And according to these graphs, we can say that, and also in the horizontal line is the Borner distance. The relationships, the outcome from this analysis was that the relationships for the GMPs derived for Turkey give a much better result as we expected. But the GMPs derived for using the international records like peer, let's say, most of the methods are developed using the peer. They were not capturing the behavior, or so the stations, station records are much more close when we use the relationships derived for the Turkey. So you can see the damp response spectra with the design spectra of the Turkish earthquake code. It's a simple relationship. Okay, I forgot to put the graph for that, but you can check, and if you have question, I can send it to you. This is the Turkish earthquake design spectra, and these are the records obtained from the stations. So the other important point in the one earthquake was that the aftershocks, there was one big aftershock. If I don't remember wrong, it was around 6.5 magnitude, and it struck the damaged buildings. Okay, and after the main shock, let's say after the earthquake, the aftershock, the first big aftershock, struck the buildings and damaged the moderately damaged buildings before the aftershock. And you can see these aftershocks map on the figure. This is the epicenter, and this is the locations of the aftershocks. And in the second figure, you can see the damage on the village. Okay, these are the places that we visited to observe the damage that occurred in the village. And the other important part, the site observations give a huge coincide, let's say. They are so consistent with the fault solutions, and aftershock distributions clearly indicates the same pattern, like 60 to 70 kilometer long northeast and southwest trending fault plane. And there are some damage structures in the slides now. These are the unengineered village buildings. They damage mostly, as you expected. In this slide, you can see the total collapse, severe damage, and moderate damage, light damage, and undamaged structures according to the site observations and according to the number of stories in this slide. And when we look at this figure or this table, we can see that the most damage happened, let's say, around 3 to 6-story buildings. So these are the moderately high reinforced concrete buildings, actually. And this is the site observations that we obtained from the statistics, let's say. This is the red one shows the total collapse, the orange severe damage, and the yellow one is the moderate damage, the green one light damage, and the gray one is the non-damage. The damage statistics in the A, this is for the one city, this is for Erciş, and this is for together. So why the one and Erciş are separated? Okay, they are the two main locations for the earthquake strike, especially for the main and aftershock. So these are the bridges. We can say that during the earthquake, the bridges are performed well. Okay, only in few of them there are some shear K problems at the isolation part, and there are some small crackings, but in the total, most of them was performing good, except only few one like this one, but still it doesn't collapse. And the tunnels also in good condition. Okay, they also didn't suffer. And this is the historical structures. They are located on this region. Okay, this is the Akdamar church. Okay, it's a very old historical structure. It's located inside of the lake. Okay, there's a small island on the lake, and this structure is located on it. And there's one historical bridge and another historical tomb, let's say. So we have looked at these 3 historical buildings and look at their backgrounds, how many earthquakes that they have experienced during their lifetime. And these are the earthquakes that we obtained from the literature. And the first one is the tomb, the Kadem Pasha Hatun tomb, and the second one is the bridge, evil bridge, let's say, and the third one is the church. So you can see 2 figures from one of them before the earthquake, and the second one is after the earthquake. And this structure is also giving an idea about the direction of the earthquake. Okay, you can check the paper that I shared. Okay, we use these damaged structures to be able to obtain the fault mechanism also. Not only one, of course, altogether. And this is the Shaitan bridge, or evil bridge in other way, and it performed well also. Okay, there's no a big damage. And this is the historical church. There are some small cracks inside of this church. You can see here, and this one, let's say. But they are not the major ones, let's say. So the acceleration and the velocity time history is recorded at the closest station to the source, like Muradiye, do not show clear source effects in the study. And the ground motion at Bitlis is likely affected by the site amplification at high frequencies, like greater than 1 Hz, as suggested by HVSR calculated from the aftershock recordings. And the comparison of the observed ground motions with GMPEs suggests that the one main shock produced on average relatively low peak acceleration values. And furthermore, it's found that the decay of the PGA with distance is better captured with the Turkish GMPs, as I mentioned. So from the initial surveys on the spatial distribution of the rural damage observed a potential hanging wall effect associated with the greater levels of damage on the hanging wall parts of the fault compared to the foot wall. And despite the lack of quantitative evidence due to spare recordings, the author observed, we observed that a similar distance from the epicenter or fault plane with similar site conditions. There are variations in the anticipated ground motion levels. This fact suggests improvements in the current ground motion prediction equations, as not all of them consider hanging wall directivity or basin effects. And also it's observed that the fundamental periods of heavily damaged mid-rise residential buildings were in the vicinity of the computed peak spectral accelerations from the measured ground motion data as clearly as we expected. And the bricks are observed to have minimal damage as targeted in design, even though they are located within the proximity of the fault. And tunnels and dams have no damage. And similar to the bricks, the cultural heritage structures that were 500 or more years old were observed to have minimal damage because of the simple design detailing, and the focus on high rigidity was used for these structures, allowing them remaining intact during the earthquakes. So this was the first part, and now I will talk about another studies that we made for school buildings and historical structure. Actually, this is the only one. It's a huge area. Okay, there are many big variety for the historical structures, and therefore it's not possible. Sure, there are some students. Okay, but first I have to figure out how to allow you to answer, talk. Can you help me? Because I can't see the chat boards.
We are working on chat box. Meeting.
Where? Okay, you can ask. I can listen.
Dr. Vishal, can you continue your presentation? The second part of your presentation.
Okay, just which slide did you set?
No, historical structures. Second part of your presentation.
Okay, so I will start. There was some students who tried to ask questions. That's why I interrupted. Okay. So let's continue. This is the second study that we made with my colleagues. Okay, the last one is my advisor at the PhD, and the others are friends from the Middle East Technical University. It's a big university in Turkey, and it's a good university. And this is the another international conference for the earthquake engineering taking place in Turkey. And if you didn't contribute it, I highly recommend you to contribute in the following years. So it's a nice and advanced conference. So in this conference, we studied the comparison of the seismic hazard maps. Okay, I mentioned that they were new. It's new for Turkey, and we investigated based on the spectrum intensities and corresponding engineering demands with a case study with the RC school buildings located in Istanbul. So it's not a big fail, let's say, to see the structures in earthquake structural damage, especially the collapse in the big earthquakes. Okay, but if you have a bad structural stock, let's say, this happens unavoidable, and this due to unsatisfactory structural performance of school buildings. We see many collapse school buildings, especially in the previous ones like Marmara, Düzce, Bingöl, Van earthquakes, and their catastrophic results. Several countrywide projects had been initiated. So after these big earthquakes, as you heard, like Düzce, okay, many projects had been initiated related with that. ISMAP, JICA were a few of them. These are the another related studies that we made for these school buildings. Okay, I will only show you just one part of that. At first we performed a database. We created a database, and in the second hand we observed the performance of these school buildings individually. We obtained the fragility curves for these structures, and then we obtained the fragility curves also for the aftershocks, okay, not only the main earthquakes. And then in here, finally, I will show you the comparison with the previous earthquake code and the recent one in terms of the ACI. Why we use the ACI, I will mention in the following slides, but let's say, just a minute. Okay, the ACI is the acceleration spectral intensity, and it gives you a big range to investigate the damage pattern. So in here, we observed 321 reinforced concrete school buildings. Okay, they are previously assessed by using the earthquake code, let's say, with the World Bank program map. And 36 buildings had been selected as a database for the study, and mostly these are the index for the database. So the construction year was between the 1933 to 2005. So it's a huge range, a big range, let's say. And the second one, the average plan area is the 475 meters square. The average story height was 3.3, and the average distance to the fault is like 19 kilometers, and average concrete compressive strength is 10.21 megapascal. The average steel tensile strength is 253 MPa. As you can see, the average concrete stress is less, and mostly this is lesser, you can believe, and therefore the school buildings damaged so much during the earthquakes. And where are these school buildings? They are located in Istanbul. Istanbul is the one of the big cities located in Turkey at the west part, okay? Let's say west north. So we performed some other studies, and in this study we have created the new hazard map with respect to the other, by looking with the ACI parameter ranging from 0.1 to 0.5 seconds, like firstly given in the literature by Hausner, let's say, and in the second one is the 0.1 to 2.5 seconds range. And the first one is mostly used for the dams because, as you can see, it's kind of rigid structures, and therefore Yakut et al. Studied and observed that using this ACI parameter between the range of 0.1 to 2.5 seconds gives a better match with the purpose, let's say. So what is the motivation? Okay, we wanted to see the reflection on the expected structural performances because of this new seismic hazard map. So we have 3-story buildings. So we took only the 9 buildings from the database and work on that. You can see the map for the buildings. Okay, there are 3-story, 4-story, 5-story buildings, and this is the index for that. These are the locations. Okay, the locations are important to obtain the NIV design spectrum according to the NIV hazard map, and you can see the details for the soil conditions. So in the slide, you can see the general characteristics for the structure, okay? For the structures like multi-degree of freedom systems, yield displacement, ultimate displacements, model mass, and model stiffness values. Why we gave this? Okay, because we have created the STO of these buildings and run the time history analysis with respect to these single degree of freedom system. So in the purpose, we only check the roof displacement as a performance criteria. And these are the fragility curves obtained from the previous studies. Okay, you can see this is for the 3-story and 4-story buildings. You can see the fragility curves, and as you when you look at the graph, okay, for example, for a velocity of around 60 centimeter per second, almost 55% will is expected to collapse. It's a huge damage for the school buildings, and we need to take precautions for that. We also extended that study and obtained the fragility curves for the main shock, let's say, for the main shock and aftershock sequentially. So we run multiple analysis and obtain the performances of STO systems, and obtain the fragility curves for 2 directions, which are showing the main shock and aftershock on 2 axes with a 3D map. So, and these are the contour plots. Why this is important? Let's say one earthquake happened, like in one, okay? In one earthquake, the main shock was around, let's say, 0.2 G and let's say 30 centimeter per second. So it was around here, but the second one was also close to that one, okay? It was 0. Let's say if you made a seismic hazard map and if you succeed to obtain the aftershock, possible aftershock PGV, you can easily say that looking at these graphs, my expected damage will be somewhere here, and it will show me the expected immediate occupancy level. Okay, this is just direct implementation of this 3D plot on 2D. These are the contour plots. So after these studies, as I mentioned, we try to investigate the effects of this spectral design spectra change, how will affect our results. We try to observe that. And in here, you can see the Wontan et al. ACI parameter. It's also used by the Hausner. I made a mistake, I think. They mostly use this ACI parameter for the dams, actually, okay, for the rigid structures. So the Yakut et al., Yakut and Yilmaz, let's say, used a modified ACI parameter to be able to obtain an extended range, okay? So we need to make some compatibility to be able to use the sites, okay, or to compare to spectrum with respect to the site conditions, and this is the comparisons, okay? These are the equivalent of the soil class. So this is the NR A, B, C, and D, let's say. So in here, first, I want to show you the ACI ratios, which are calculated for each building. In this table, you can see 9 buildings and their X and Y direction. And in here, the site conditions, let's say, and this is the periods, okay? And this is the ACI and ACI modified parameters according to the previous earthquake code and the new one, let's say. And by the way, our new code is a little bit looks like, especially the seismic hazard map and design spectrum derivation looks like to the ACI 318. Okay, there are some small details, but in the general, in mostly they are same. Let's say they look like to each other. And this is the soil classes, and this is this plot spectrum for the new one, and these are the ACI ratios. When we look at the ACI ratios, okay, and for the main one and modified one, most of the new codes show us there will be an increase in this ratio. So if yes. Do you have a question?
Anybody have a question? They can raise your hand or I'm the university, but you can pose the question to the stage.
It's so hard to understand because I can hear the echoes behind your voice. If I succeed to open the chat boards, I can answer your questions. Yes. Let me finish the presentation, and at the end you may ask all the questions, okay? Then we can find the way how to open the chat board, and I can understand you clearly, okay? Sorry about that, because there's a big echo behind that, and I can't hear you. So, and these ACI ratios are higher, let's say. So we are expecting more damage as expected from the basic earthquake engineering details. So the ACI ratios are generally smaller than 1 for the earthquake zone 1 plus site class Z2, okay, the modified one, and also the modified one. These are the, let's say, good soil conditions, but we experience also higher ratios with the soil class 2 and also the earthquake zone 1. So by the way, in the NEEP code, we don't have the earthquake zones, okay, we have direct seismic hazard. In the first one, it was a zonation map, and the new one is a seismic hazard map. So we try to make it compatible. And for short period systems, code spectrum based SIE ratios are compatible with the ACI ratios. And like this one, let's say, whereas for medium to long cases, the ACI ratios are close to the ACI modify, let's say, or ACI star. For long period systems, SAE, the spectral acceleration, elastic spectral acceleration ratios are affected due to the conservative definitions of the descending part of the design spectrum, but by the earthquake code. So the main change happened in this part. In the first one, it was given with the tree formula, okay, then they changed it, okay, they added a TL and also the T1, let's say, and we have now 4 formulation or 4 equation to drive the elastic spectrum, and this part is highly effective solutions, okay? So this, and I can say that this is much more realistic than this one. This is a little bit higher. So for real ground motion records, the Pierce NGA West 2 database is utilized, and we choose the ground motions according to the code, the 7 for the previous one and 11 for the new one. So these are just the rules. These are done according to the rules from the earthquake codes, let's say. So totally for each building, we drive 18 records and 18 time history analysis. And these, the details of these ground motions are like this. The magnitude range is changing from 6 to 8, and fault type is relevant with the location, like strike slip. And generally, okay, sometimes we need to add other ground motions because of lack of data. And then VS30 also 300 ranging from the for the site Z2 and Z1, let's say. These are the, you can directly check, I think, with the NR, the like B and C. The selected records are fitted to the target spectra by amplitude scaling in the time domain. So overall scale factors are checked to eliminate very large or very small scale factors, and it's ranging between the 0.79 to 3.86. And for each building, these design spectra are derived, and selected ground motions for each building are obtained because our period range is changing, and then depending on that, for each building we have to choose the new earthquake ground motion set, let's say. Then we look at the mean spectrum SAE ratios and check them with the ACI parameters. Okay, they are mostly look like to the ACI modifiers. I have to say that. So the elastic spectral acceleration ratios reach to 1.56, and the mean spectrum base ratios are around 2.24, like this one, and 2.28 for two buildings. Okay, so it means that yes, we can use the elastic spectrum for the structures, but if your structure is too important, okay, and or have a special purpose to construct that, okay, you have to run a site-specific, you have to obtain a site-specific design spectrum, okay? You have to perform some seismic hazard analysis for that. And based on the nonlinear static pushover curves, as we performed previously, we obtain the SDO for each building, and then run the nonlinear time history analysis for the structure using the OpenSys platform, and employing these two code-based record sets, let's say. Then we obtain the peak roof drifts and base shear, and obtain the three performance level according to the pushover analysis, and checked our performance level looking at these roof drifts. You can see the roof drifts in here. Okay, the red ones shows mostly higher than, okay, and this the green one means that they are less, one or less than the expected. And you can see the performance levels. Okay, most of the structures, as you can see, collapsed. Okay, they are in according to the new one, let's say. This is the old one, and this is the new one, let's say. Most of the structure collapsed, and here the CP means the collapse prevention, and in here LS, it means life safety, as you expected, and if it's passing the collapse prevention, we assume that it's collapse. The interesting thing on this part is that we were expecting some more collapse building in here. Sorry. Yes. On this part, let's say. And it's because of having higher acceleration. So in here, when structures falling into the medium to the long period range are examined, since the former code yields much more critical values in this region. So actually, we were expecting some more collapse buildings here, but it was a little bit surprise to us. So the engineering demander parameter considered are generally lower as compared with the mean spectrum-based elastic spectral acceleration ratios, and partially with code spectrum acceleration ratios, and the resulting performance levels are mostly collapse prevention for these cases. And we can say that most of these CPs can be named as the collapse also, okay? So we are expecting more damage with the new code. We also check another Okay, we reperform the analysis by scaling with the 2 to 3, like 0.6067 scaling factor, and observe that they are close. The findings are obvious, okay, because it shows that yes, if you have a decrease 30%, you can see the new code will give you more collapsible links than the other one. This is just extra effort, okay, actually means not so much detail, not a big thing, just we wanted to see how it will be affected, okay, we want to catch this graph. So overall results reveal that although the performance levels at the end of the assessment studies for the examined cases turn out to be similar or slightly changed, the spectrum intensities and the resulting engineering demand parameters are highly influenced by the seismic code. And the numerical comparison implicitly pointing at the probable need for additional retrofit requirements for Istanbul-based school buildings falling into short to medium period range, if not marked as collapse or collapse prevention already. Okay, so we are expecting an earthquake. Okay, we are in few years, let's say, in the Istanbul, and okay, I can say that we didn't take so much precaution for that, okay, due to lack of money. And I hope it will not become like this, but this is the reality and this is the expected results for that earthquake scenario. Okay, sorry to see these results. And the last part will be related with the seismic risk assessment for the historical structure. As I mentioned, if you are looking at the historical structure, it's a big area and it's hard to study, or it's hard to mention every detail, okay? So in here, I will show you only one stone masonry minaret, okay? It's located in Diyarbakir, which is my hometown. And if you want to look at the details, this is the paper for that one. You can check the details. The interesting side of this minaret, it's standing on 4 legs, okay, 4 piers, let's say, 4 column. And these columns are the main rectangular part is freestanding on these stones, okay. It's more than 500 years old, as you see, okay. It's coming from the Akkoyunlu Turkmens period, okay, according to the inscriptions written on it, okay. So it's used as a minaret. It's belonged to the mosque in the way. And this is the architectural drawing for that one. You can see in the inside there's a cylindrical staircases. Okay, the main part is rectangular. The interesting part of this structure is that the rocking behavior becomes much more important, okay? And therefore, under an earthquake, you have to derive this rocking behavior, or you have to consider this rocking behavior firstly, okay? So first we try using the solid upper body, okay, without any contact definition, and look for the rocking angles, okay. And on the next part, like in this study, then we use the contact definitions between the stones, okay. Each stone on this part, especially upper parts, are not that much important in terms of rocking behavior. When we look at the mode shapes, you will understand why. And these parts, the collapse is expected on this region mostly. Okay, maybe an earthquake, you may expect some damage at the upper part also because of this cross-section change. Okay, this is the structure. Okay, there is some crackings at the one of the main beams. Okay, that was the purpose to study this structure actually. Okay, Diyarbakir is located. It's not located on a very high seismicity region, but there's a near fault named as Lice, okay, and the earthquake happened there, affects Diyarbakir also, okay, and we wanted to use this structure is a seismograph, okay. We want to observe that what is the maximum PGA that this structure can survive, and if the earthquake happened in here, okay, they has to be less than this PGA, okay? So it makes it like a seismograph. So this is the location, okay? This is Diyarbakir, it's my hometown. And this is the Lice, one of the big earthquakes happened here and affected the structure. But the cracks is not only the results of the earthquake, let's say, okay, is actually mostly because of the construction, okay, happened in that region, and also the car traffics, okay. So the historically Lice area has been very quiet. After this earthquake, Diyarbakir was located in second hazardous zone, and the maximum PGA, expected PGA, will be around 0.33 G. Actually, this was for the previous earthquake code, according to the previous earthquake code. Maybe in the new one, it may change. We didn't check that yet. So the minaret in Diyarbakir is located 75 kilometers far away from the Lice, and therefore we use the GMPs to be able to obtain the possible PGA values for this structure and observe that it will be around 0.5 G and 0.06 G respectively, okay? According to these two fault. Okay, we can't see the Lice record, okay? It's an historical earthquake and it's not instrumentally recorded. Yep. Okay, so then we choose some compatible one from the peer database with the same faulting, with same mechanism and with the same magnitude, let's say. And then according to the direction, okay, this is the north one, this is the east one, and this is the crack that happened. So coupling of directions and yes. Just a few more slides, okay. So, and this is the model that we used, Elestina, ANSYS Elestina, and according to that, we define the contact surfaces, and also we define the material brittle damage pattern. Okay, you can see the details in the paper. Okay, this is the material model used for these solid members. And after running the time history analysis, we observe the damage. Okay, we succeed to capture this damage or the stress location, concentrated region in the models, and it's show us also the why the structure cracked in that part. Okay. And so we can say that if you know the distance to the fault, and if you know something happened because of an earthquake, okay, it may increase during time due to the traffic, but the main reason was the earthquake. So you can observe where will be the damage according to this information using the GMP relationships. So that's all that I can show you today. It was a condensed lecture. I know I talk about many things. I hope it was clear to you and you enjoyed the lecture.